of North Carolina at Chapel Hill in 2009, where he is now professor of chemistry. Since 2018, he has been an associate editor of Synlett. His current research focuses on new reaction development by harnessing the power of organic photoredox catalysis. Okay, so yeah, welcome, Dave, and the floor is yours.
Okay, thank you, Catherine. Good morning, afternoon, or evening, wherever you're joining us from. We're glad you're here. We're excited to host this WebCheminar on photoredox catalysis. And so, right, I think a lot of us know that photoredox catalysis has certainly become a hugely popular area in organic synthesis and catalysis over the past decade and a half or so. And so, you know, it's been a great topic for some Synlett clusters. And so I hosted one last year to honor Professor Shinichi Fukuzumi's 70th birthday. And of course, Shinichi Fukuzumi has made important seminal contributions to the development of organic photoredox catalysts. And so we, you know, wanted to honor that and come with a special issue of Synlett. And so today we have two groups that contributed to that issue that we elected to invite to talk a little bit more in depth about their chemistry, and we're excited to have them here today. Right, so I'm going to keep the introductions brief here so that we can hear more from the speakers. So you can go ahead and bring up Todd's slides here. So our first speaker today is going to be Professor Todd Hyster at Cornell University. Todd is a native of Minnesota. For those of you that might not know where Minnesota is, it's sort of that frozen tundra in the center of the United States, all the way in the north, okay? It gets very cold there in the winter, but it's lovely in the summer. Todd's from there. He did his undergraduate work at the University of Minnesota and then moved to Colorado State University to do his PhD studies with Tom Rovis at Colorado State and completed his graduate work there. He then, actually, I should say, during his time with Tom, I believe he spent some time at the University of Basel with Tom Ward, learning about metalloenzymes for CH functionalization. And I think that's probably where Todd's interest in using enzymes to catalyze reactions really got started. And so that sort of convinced him, I think, to move to Caltech, where he did his postdoctoral work with our recent Nobel laureate, Frances Arnold, in the 2008, or sorry, I forgot the year here. But once he finished his postdoctoral work with Frances, he started his independent career in 2015 at Princeton University and really established an exciting research program developing new enzymes to catalyze asymmetric transformations, and particularly focused on enzymes with organic flavin cofactors. And so that's why I thought he was an appropriate invite for this cluster on organic photoredox catalysis. He recently moved to Cornell University in 2021 and is an associate professor of chemistry there. So Todd's won a number of awards. I just, highlight a couple recent ones, the Arthur Cope Scholar Award just this year, and also the Amgen Young Investigator Award last year. So with that introduction, Todd, we're happy to have you here today, and we're excited to hear from both you and your student Bryce Nichols in terms of the chemistry that you all are doing.
Great. Well, thanks, Dave, for the really kind introduction and for the opportunity to share some of my group's research in the area of photoenzymatic catalysis. And so hopefully you can tell from my background, we really are, I think, synthetic organic chemists. And so we're ultimately interested in reactivity and developing new organic transformations. And we just happen to use enzymes as the scaffold on which we build these new reactions. And so I think when you're thinking about developing new catalytic reactions, you're obviously going to gravitate toward catalytic platforms, and depending on the platform, it'll sort of dictate how you think about certain catalysts developing new reactions, right? So if you are interested in, say, using transition metals for new transformations, you can take advantage of the fact that transition metal catalysts are substrate promiscuous, and they have access to a few different fundamental reaction mechanisms like oxidative addition, migratory insertion, transmetallation, among a few others. And so you can take advantage of the substrate promiscuity with these basic mechanisms, use them in different orders, and you gain access to hundreds of new types of chemical transformations. Now you can do the same thing with organocatalysis, where you can use an amine, for instance, form an enamine, aminium, or singly oxidized enamine. Again, exploit the substrate promiscuity of the catalyst to again gain access to hundreds of new chemical transformations. Now, in the area of biocatalysis, we tend to take a different strategy, and that's because we tend to take enzymes from nature. And we tend to think of enzymes in nature as being highly specific for a single reaction mechanism. And this is sort of indicated in how we name enzymes. So for instance, a ketoreductase, we know that enzyme will catalyze ketone reduction. We know that it does this via a hydride transfer mechanism that maybe looks very reminiscent to how you would do, say, a carbonyl reduction using organocatalysts. We know that ketoreductases are substrate promiscuous, but we tend to think that they can only catalyze this one reaction mechanism. And so the question in my group has been, can we take a page out of small molecule catalysis and develop new types of reaction mechanisms for existing enzymes, and hopefully then be able to use the tools of directed evolution and molecular biology to hopefully solve some challenges. And so of course, we're not the only ones interested in doing this, and I think it's useful to consider the reactive intermediate that you want to use to understand the mechanism or the enzymes you're going to gravitate towards. And so, for instance, if you're interested in organometallic intermediates, then you're going to be gravitating towards metalloenzymes, whether they be natural or artificial. And what we've seen over the last 40 or 50 years is that metalloenzymes can catalyze a number of different transformations, right? Where the metal is really responsible for the reactivity, and the protein scaffold is there to influence the reactivity of the metal, but mostly provide a chiral scaffold. If you're interested in closed-shelled intermediates, then you're going to be drawn to hydrolases, to telomerase, and aldolases, which will catalyze, I think, a number of classic transformations in organocatalysis. And so when my group started in 2015, we became interested in whether enzymes could use other types of reactive intermediates. And in particular, we were drawn to the reactivity of organic free radicals, right? So free radicals, I think, are really incredible intermediates in that they're very high in energy. And what that means is that they can mediate a number of different bond-forming events with relatively low activation energies. And I think this is in part why photochemistry and electrosynthesis have become such important tools to synthetic organic chemists over the last decade. Now, of course, the challenge falls in trying to achieve selectivity in these transformations. And that's because when you have reactions that have low activation barriers, it can be difficult to achieve energetically meaningful differences in the diastereomeric transition states. And as a consequence, small molecule catalysts developed to address selectivity challenges involving free radicals are underdeveloped by comparison to other reactive intermediates. And so the goal in our group has really been to see if we can find ways to form radicals within protein active sites. And if we can do that, then use protein engineering to render these types of transformations asymmetric. And so the protein that we're going to talk about today is this enzyme called ene reductase. This is also referred to as old yellow enzyme. It was the first isolated and characterized flavoprotein. It's found in some natural product pathways, but it's largely thought to be overexpressed in response to oxidative stress. And we know synthetically it can reduce activated alkenes with high levels of selectivity. Now, there's a few features of this enzyme family that I find to be attractive. Maybe the first of which is that you can buy collections of these enzymes from your favorite enzyme vendor. And what that means is that if you don't have experience expressing proteins, you can imagine recapitulating some of the reactivity we're discussing today using a commercial kit. Now, these enzymes have very broad substrate scopes. And so you can see here on the left, these enzymes can accommodate a variety of different electron withdrawing groups to activate the alkene for reduction. On the right, you'll see alkenes within a variety of different chemical environments. And so the hope is that this substrate promiscuity should help promote catalytic promiscuity in much the same way that substrate promiscuity promotes catalytic promiscuity with small molecule catalysts. Now, the native mechanism does not involve radicals. It's a simple hydride transfer mechanism. You can simplify the ene reductase active site to 4 key components: flavin in its hydroquinone oxidation state, 2 residues to bind, orient, and activate the substrate, and a conserved tyrosine. And so what happens is the substrate binds, it's rendered more electrophilic, hydride is donated to the electrophilic beta position, and then that tyrosine functions as the proton source to give you your reduced product. At this point, the product will leave an equivalent of NADPH, will move into the protein active site, donate its hydride to flavin, and now you've primed the enzyme for another catalyst turnover. And so within these enzymes, flavin's moving back and forth between the hydroquinone and quinone oxidation states. And so our question was, could we think about doing radical reactions within that protein active site? And one of the early transformations that we were looking at was the radical cyclization of this alpha-chloroamide to provide a chiral lactam. This would solve what we viewed to be a long-standing challenge in synthetic organic chemistry, and would also represent a new biocatalytic CC bond forming reaction. And I think this is really important. If you look at how biocatalysis is used today, by and large, it's for functional group interconversions. And so if we want to be able to exploit the attractive features of biocatalysis more broadly in organic synthesis, we need new CC bond forming reactions. And so our hope is that we could solve that problem here. Of course, the challenge is that when we subjected this substrate to our collection of enzymes, none of them were able to catalyze this reaction. We just observed unreacted starting material. And this is because if you look at the reduction potential of the substrate by comparison to the oxidation potential of the flavin cofactor, what you'll quickly notice is that electron transfer is uphill by over 25 kcals per mole, meaning practically this electron transfer isn't going to occur. And so we needed some mechanism for making flavin more reducing. And I think we were really inspired by the studies by Fukuzumi, looking at flavin type analogs and their photochemistry to access more reducing excited states. And so the thought was fairly simple. Let's take the same enzyme, same substrate, and now we're just going to radiate with light. And what we found immediately was a step change in function. If you use 390 nanometer LEDs, which should closely align with the absorption spectra of the flavin hydroquinone, we now see 60% yield of a 2-to-1 mixture of the cyclized to reduced product, promising levels of enantioselectivity. And what we found in optimizing the reaction is that when you move to 497 nanometer cyan LEDs, you actually get higher yields, better selectivity for the cyclized product over the reduced product, and good levels of enantioselectivity. And so we looked at the substrate scope of this reaction, and what we found is that it's reasonably broad. So the enzyme will accommodate a variety of different aromatic substituents off of the alkene, but it also accommodates aliphatic substituents. You'll notice that the enantioselectivities are a bit lower. This is a problem that can be addressed using directed evolution. We found in all of our E-red chemistry that the flavin cofactor is really effective at controlling the delivery of hydrogen atom to prochiral radicals. And so that means we can use tri-substituted alkenes and get reactions to occur with both high enantioselectivity and diastereoselectivity. And then I think my favorite feature is the fact that these enzymes can catalyze 7 exo and 8 endo cyclizations. If you were to do these reactions with small molecule reagents or catalysts, these reactions would favor the hydrodehalogenated product. And so to tell you more about this chemistry, I want to hand it off to Bryce Nichols. He's a 5th-year graduate student in my group. He contributed the work that we included in the Synlett cluster and has done some really interesting evolution and evolution and mechanistic studies on the system. And so Bryce, I'll hand it off to you.
Thanks, Todd. I appreciate that for that kind introduction. Let me just get my screen going here. As Todd was saying, us in the Hyster group, we are at our core synthetic organic chemists, and so we looked to sort of address the challenges of these cyclizations of these amides, these radical cyclizations of these amides to furnish these lactams. And I think one of the difficulties to this transformation is the slow bond rotation of the amide. So in its cis conformation, you're able to form the cyclized lactam. However, if the amide is in its trans conformation, you could get premature termination and ultimately just get to this hydrodehalogenation product. So Todd and I surveyed a variety of different radical cyclization activation modes and termination modes, organotin, a photoredox method, iron hydride, as well as photoenzymatic. And what we found was that the photoenzymatic method had a much higher degree of product selectivity. And this is ultimately because the enzyme is templating that photocyclization. So to sort of look into how this is actually working, you kind of have to go inside the enzyme active site. So as Todd was saying, the flavin cofactor is in its most reduced form, its hydroquinone form, and your substrate, your alpha-chloroamide, is going to come into the enzyme active site and bind to form this electron donor acceptor complex. And then if you photoradiate that complex, you can induce a mesolytic cleavage of the chloride to get you to this alpha acyl radical. The alpha acyl radical will then cyclize into the pendant alkene to get you to this benzylic radical, which ultimately, as Todd was describing, you can quench selectively through hydrogen atom transfer. And you turn over the system using a turnover system with NADPH and ultimately glucose as your terminal reductant. But I think if you're looking to optimize these systems, it's really important to look into the how the rate limiting step essentially is how the enzyme is able to utilize light to do productive radical chemistry. And so in order to understand that, we really have to have a strong understanding on these electron donor acceptor complexes. And the idea here is that you have an electron rich molecule, an electron poor molecule, donor and acceptor. They come together to form with large amounts of orbital overlap to form these EDA complexes. And then if you photoexcite that, you can induce a charge transfer to ultimately get you to this excited state radical ion pair. And now in these systems, the rate of the back electron transfer is quite fast. So for a while, I think from about the 1950s all the way to the 1970s, organic chemists hadn't really used this sort of phenomenon to do productive radical formation. And it was in the 1970s where they started to figure out that if you appended some sort of leaving group onto the electron acceptor, you could then do the excitation to get you to the radical ion pair, and then ultimately through mesolytic cleavage, an irreversible event, trap that radical. And this is exactly what's happening in our system. So in our case, the flavin hydroquinone is the electron donor, and the substrate is the electron acceptor. You then photoexcite to get you to this radical ion pair, and then ultimately it's through the ejection of the chloride that you get to the alpha acyl radical. But as you can see here, that every excitation event you get to, there's a competition between doing the mesolytic cleavage versus doing the back electron transfer. So even with this irreversible sort of cleavage in place, it's still not every excited state goes forward to productive radical formation. And that's due to the fast rates of back electron transfer still being present in this chemistry. So a very interesting kind of value to see an interesting number to see the efficiency of these systems is quantum yield, which essentially is the amount of product formed per photon absorbed. And in our systems, the way I like to think about it is given a particular excitation event, what is the likelihood that you'll do productive radical formation? And what's really interesting is if you compare our systems, the endoreductases for these non-natural photoenzymatic reactions to some of nature's photoenzymes, you see that our photon efficiencies are extraordinarily low. So when I was a first-year student, Todd gave me the challenge of sort of thinking about, could we engineer a photoenzyme for greater quantum yield? Could we change the active site dynamics through directed evolution in such a way that we could make our enzymes more efficient in the utilization of photons? And I was joined on this project by two really great grad students, Sarah and Dan, as well as two really awesome postdocs, Daria and Yushwe. And so we elected to do, after some optimization of the high throughput screening platform, we elected to do a simple error-prone mutagenesis campaign. And essentially this is just making random mutations across the entire gene. And we tested 1,000 different variants. And so the wild type protein can catalyze this reaction at about 19% yield under these conditions. However, if you install this T36A mutation, you see a bump in that yield. But over the course of our evolution, we were able to find a triple mutant which could catalyze the reaction in even higher yields. And so just to orient you with where these mutations are, the T36A mutation and the K317M mutation are sort of on the outside of the enzyme, and the Y343F mutation is inside the enzyme active site. And so we weren't particularly creative in our lab, I guess, so we named the enzyme G6 because we found it in the well G6. And so we wanted to correlate this improvements in activity with sort of improvements in the inherent photophysics. And again, sort of when we think about quantum yield, what we're thinking about is once you get to that excited state, what is the likelihood of doing mesolytic cleavage over simply just going back to the back electron transfer? And over the course of our evolution, as you can see, we started off with about 2.4% quantum yield. And over the course of our evolution, by tuning that enzyme's active sites, we were able to increase that to about 10.5%. And so we wanted to look deeper into the sort of inherent mechanisms behind this improvement in the photophysics. And there's sort of two reasons why we could see this more productive photochemistry. And the one could be that we're decreasing the rate of back electron transfer, or conversely, we could be increasing the rate of the mesolytic cleavage. And we wanted to tease this apart. So if we're decreasing the rate of back electron transfer, we would also be increasing that excited state lifetime. And conversely, if we're increasing the rate of the mesolytic cleavage, we would be decreasing that excited state lifetime. And we saw through our studies using spectroscopy and transient absorption spectroscopy, we were able to determine that the new variants had a much lower, a much shorter excited state lifetime. And this is indicative of an increase in the rate of the mesolytic cleavage. So what's really interesting actually is that in the wild type system, the excited state is about 2.8 picoseconds. And you can imagine through this mechanism, you go through a cleavage, CC bond formation, and ultimately a hydrogen atom transfer. And what we did is looked at the lifetime of the flavin radical intermediate, the semiquinone. And in our wild type system, that lasts for about 700 picoseconds. And in our sort of new variant that we found, this triple mutant, the excited state lasts for about 0.8 picoseconds, and then will very rapidly form oxidized flavin. And so, because we see much less radical character on the flavin itself, we think that it's potentially moving through a much more concerted transition state, where we're going from less a stepwise mechanism to something that looks a lot more concerted. And with that, I'll transfer back over to Todd, who's going to teach us a little bit more about where we've been able to take that chemistry.
Okay, great. So what I want to tell you about now is some of the new directions we've been able to go with this chemistry now that we understand a little bit more about the mechanism. And so one of the transformations that we were interested in from the very beginning was whether we could do an intermolecular reaction, right? If we really want to use biocatalysis to build important molecules for society, we need to be able to build molecular complexity by bringing two components together. And of course, the challenge is that when you have these incredibly short-lived radical intermediates, what it requires is for the radical to be in the active site and generated in the presence of the alkene coupling partner. And at first pass, looking at the native mechanism or even looking at the cyclization mechanism, it wasn't clear that we would be able to do this. And so I think in the group, we had dreamed up a number of really elaborate ways of being able to control this reaction. And I think it's really a testament to my students that they went and ran the simplest experiment first and didn't talk themselves out of it. Because what they ultimately found is that when you take the alpha chloroamide and the alkene, and use the same enzyme before under slightly modified reaction conditions, you can get the intermolecular coupling in good yields, excellent levels of enantioselectivity. They found that when you use a different ERED homolog, no stock, you actually favor the opposite enantiomer. And so in their initial screen, we were able to find enzymes that access both possible enantiomers of product in very high yields and selectivities. And so of course, we're happy to have the reaction working. But I think what was most exciting was the fact that you see less than 5% hydrodehalogenated product in both cases. Because what it indicates is that there's a control mechanism in the system that we didn't anticipate. And you can actually learn more about that control mechanism just by looking at the UV vis. So this is what the absorption spectra of the flavin hydroquinone looks like. When you add the alpha chloroamide, you see this weakly absorbing CT complex with a max absorption right around 495 nanometers. And then really to our surprise, when you take that sample and you add alpha methylstyrene, you see a significant change in the absorption species. It looks as though you now have formed a much more strongly absorbing species. Now, just to provide a little context, if you don't have the alpha chloroamide present, you do not see the charge transfer complex. And so we think this is evidence for the intermediacy of a higher order CT complex. One that when you only have the alkene or only have the alpha chloroamide present within the protein active site, forms a CT complex, but has low molar absorptivity and as a consequence isn't particularly reactive. However, when you have the alkene present, potentially you're getting some delocalization of the electron density of the alkene into that carbon chlorine sigma star. This is forming a better CT complex that has better molar absorptivity, and ultimately this is what's responsible for radical formation. And so because both components of the system are required for radical formation, we're able to get really high coupling efficiencies. We've prepared docking models and done TDDFT, and we can recapitulate what we see in the UV vis in our calculations. And so we think this is good evidence for one of these higher order complexes. And so this really opens the door to being able to think about a number of different intermolecular coupling reactions. And so one of the ones that we've spent a little bit of time thinking about recently is a coupling of alkyl halides with nitroalkanes, in the hope that we might be able to access enantioenriched alpha tertiary nitroalkanes. And then, the application here would be to hydrogenate that nitro group, get to an alpha tertiary amine. And of course, this is an increasingly important motif. And so I should mention that this work is really inspired by a lot of the beautiful work that's come out of Don Watson's group over the last decade, doing various coupling reactions with nitronates. And so we've looked at the coupling reaction. This works reasonably well, good yields, promising levels of enantioselectivity. But ultimately, what we like to think about is the mechanism. And so, of course, we had good evidence for the intermediacy of a charge transfer complex. And one of the things we started to think about was how do you think about the flavin semiquinone oxidizing this nitroradical anion to get you to the product? And so we did a little bit of reading and came across what I think is a really interesting paper by Kornblum. So Kornblum had taken these tertiary nitroalkanes, thiolate salts with light. It's proposed that you get to this radical anion. And then what they propose is that this actually undergoes a mesolytic cleavage to spit out nitrite to form a benzylic radical that can be quenched reductively. And so we looked at this and thought this was really interesting, right? These nitroradical anions are thought to mediate a number of different transformations. The problem in small molecule catalysis, right, is that the electron transfer event outcompetes mesolytic cleavage. But in a protein, we have this incredible scaffold for being able to control the kinetic profile of a reaction. And so presumably, with a little bit of interrogation of E-red homologs and maybe some protein engineering, we could find systems that would favor mesolytic cleavage over electron transfer. And so that's exactly what we did. We ended up collaborating with our friends at Prosomics. This is a biocatalysis company based out of the UK, and found this enzyme CSAR that's able to do this reductive coupling in good yields, excellent levels of enantioselectivity. You could imagine a number of ways of accessing this product. One might be actually formation of the nitrated product and then elimination. And so we were able to rule that out when we use phenylnitromethane, because what we end up observing is a one-to-one mixture of the nitrated and denitrated product. And so we can isolate the nitrated product, resubject it to the reaction conditions, and see that it is not an intermediate on way to the denitrated product. And so it seems to support this idea that we're forming the radical, it adds into the nitronate, undergoes mesolytic cleavage, and then selective hydrogen atom transfer to access the product. And so we think this is the beginnings of maybe an area where we can start to think about using biocatalysis to do cross-electrophile couplings and make, stereochemically complex CSP3 bonds using enzymes rather than, say, transition metals, which we think is really exciting. Just to give you a taste as to where things currently stand on the mechanism, typically we have to have some sort of electron stabilizing group off of the nitroalkane. So aromatic groups work quite nicely, but you can also use esters. And then we can use a variety of different amides, esters, and actually ketones for the alkyl halide. And so it looks like this is going to be a reasonably general way of doing these types of reductive couplings. And so with that, I just want to conclude and say I think there's all sorts of really interesting opportunities to use light with enzymes to do completely new types of transformations. And so I'm really excited to see what our group and other groups are able to do in this space. And with that, I just want to conclude by the people acknowledging the people who did the work. Kyle, Simon, Jin, and Dan were really responsible for the photoenzymatic cyclization. As Bryce mentioned, Bryce and Sarah were really the drivers behind the protein engineering project. Intermolecular alkylation was done by Claire, Simon, Jacob, spectroscopy done by Dan, and then this work was done in collaboration with our friends at Celgene at the time, now BMS, and so a big thank you to Kevin, Evan, Alyssa, Kurt, Mike, and Larry. The nitronate chemistry was done by Hagen, Bill, Tianjung, and then this was done in collaboration with our friends at Prosomics, and so a big thank you to Simon, Mimi, and James. And with that, I just want to thank the rest of my group, thank my funding sources, thank Dave for inviting us to participate in this webinar, and I'd be happy to take any questions you might have.
Okay, thanks Todd and Bryce. Awesome talk, fantastic results. If you have any questions, I believe I just have one in the chat. Certainly now's your time to chime in and send any questions, but I'll read the one question I have from the audience so far. Regarding the alkyl halide chemistry, the question is, do other halides besides chlorine work in this chemistry, such as, bromide or iodide?
You want me to take it?
I do.
Okay. So we have been able to do alkyl iodides before, and the bromines also work, but the bromines often can work in the dark in some of the systems. So the gating mechanism for sort of the enantiomer selectivity isn't as it often isn't as controlled in the bromine systems. I don't know if you have other things to add to that, Todd.
No, I think we've also seen that redox active esters can work in these reactions, which is great. And we're currently in the process of moving away from alpha halocarbonyls. And so I would say keep an eye out for some work that'll come out of our group in the next, hopefully 6 months, that'll really allow us to expand how we think about using this chemistry.
Okay. Are there any other questions from the audience at this time? Yeah, so I think the organization of the transition state where you have both reactants and the catalyst is fascinating. Sort of, it seems like pi surfaces are obviously key to that. What about aromatic? So have you looked at aromatics as part of the sort of reaction or sort of reactants that would organize in that transition state? Do you think you can actually start to think about arylation chemistry in terms of some of your, enantioselective catalytic transformation?
Yeah, that's an interesting question. Oh, Bryce, no, you go ahead and take it in.
Okay, so I honestly firmly believe that we would be able to do sort of arylations and things like that, but honestly, it's not something that we've explored because I think a lot of work has been done in that area, and so we've typically Todd doesn't let us run this reaction. So I've pitched some of those ideas to Todd before, and he's been like, no, don't do that. That's not that interesting. So I'm sure the systems could do it.
I'm really good at picking on interesting research areas. I have one other question from the audience. Is cross-electrophile coupling of halides explored in photoenzymatic catalysis?
Yeah, not as far as I know. I think, right, the challenge is that you need some way of, if you're going to use, alkyl halides, you need some way of converting the alkyl halide from sort of an electrophile to either a radical or some sort of nucleophile, so that it can end up reacting with another radical. And, normally we would think of transition metals as the right way to do that. Yeah. It doesn't seem as though nature has alternative mechanisms. That being said, I think this is where organic chemists can really step in and push enzymes in new directions, right? I think a lot of organic chemists are thinking about reaction mechanism and how to do new types of bonding reactions. And I think if you're able to bring that know-how to biocatalysis, you can really do some interesting things.
Okay. Any other final questions? I don't think I see any in the chat. Great. Well, thank you again, Todd and Bryce, for a really fantastic presentation and being a part of this webinar today. Appreciate it.
Thanks, Dave.
Thanks so much.
All right. All right. Catherine, are we ready for the next chapter here? It looks like we are. Okay. All right. So for the second half of our webinar today, really pleased to have Professor Hans-Achim Wagenknecht. And I really hope I pronounced your name, Hans, correctly. Actually, I think is this the first time we've actually met in person? Well, not in person, but
yeah, no. We met actually in Potsdam. There was a Beilstein conference on Photoredox catalysis a couple of years ago.
Yeah, I was trying to remember if I had met you at one previous point, because I'm, of course, very familiar with your research. But good to see you again, if not in person. Great. So Hans did his undergraduate work at University of Freiburg and finished his degree in 1995 with Jochen Lehmann. He then went on to do his doctoral degree at University of Basel with Professor Vogan. Is that the correct pronunciation? Okay. Meine Deutsch ist nicht sehr gut. Where he did some graduate work in glycosidase inhibitors. Following his graduate work, he moved to the U.S. all the way to Southern California to do postdoctoral work with Jackie Barton at Caltech, and then started his independent career at the Technical University of Munich in Germany in 2000, and did his habilitation there. In 2005, he started his independent career at the University of Regensburg in Germany, and then since 2010, he is now the chair of organic chemistry in Karlsruhe Institute of Technology. So Hans's research program is quite broad, and a number of different foci, including bioinorganic chemistry, fluorescent imaging, DNA, architectonics, and also photochemistry and photoredox catalysis. And certainly Hans has contributed some really beautiful chemistry, Hans and his group, involving small molecule organic photoredox catalysts, which is again exactly why we invited him to contribute to the Synlett cluster. I think he is being joined today by two of his students, which is great. I think we're going to hear about some of their small molecule organic photoredox catalysts today, and so I'll stop there. And again, thank you, Hans, for joining us today, and we're excited to hear about your research.
Okay, one moment, Professor Wagenknecht. The presentation is not in present, not yet. No, it's two. We can see. Okay, now it's perfect. Yeah, thank you.
Now you should see it, right?
Yeah, looks good. Thank you.
Okay. First of all, let me thank you very much, Dave, and also the Thieme publisher company for inviting me. And I'm especially happy about the fact that I'm recognized now as a photoredox catalyst person, since my background, as Dave already mentioned, is in field of bioorganic and chemical biology and so on. Now, I would like to give you a brief introduction to, the slides are not moving. To what we are doing actually in our laboratory before I hand over to my two doctoral students to be more specific and give more examples about the reactions. Now, I don't want to introduce to you the principle of photoredox catalytic cycles. You see that on the screen here on the slide here. The basic idea is to activate organic compounds, organic molecules by a photo-induced electron transfer that gives you a radical anion or a radical cation that undergoes a conversion to a product, and after that, a back electron transfer actually closes the cycle. Our general goals in this field is to enhance the understanding and also the sustainability of that principle by using the light more efficiently than the others, by using organic dyes instead of transition metal complexes, and also by the concept of photozymes, which are photocatalytically active peptides. And of course, we would like to explore new reactivities, and I'll give you a very brief example how we can actually activate SF6 sulfur hexafluoride in order to get SF5 organic compounds. Now, one of the points is the usage of light, and we, together with Eberhard Riedle at the LMU in Munich in Germany, we use a machine, what is called the quantum yield determination setup, in order to measure precisely the incoming light into a photoredox catalytic sample. And with that, we can actually calculate the so-called chemical quantum yield or reaction quantum yield. It depends on the literature, what phrase you are using. And this is the ratio between the number of product molecules and the number of absorbed photons. And this gives you actually a very precise information about how much light actually is used for the photoredox catalytic reaction. And there are two mechanistic regimes. One is that the quantum yield is below 1, and then you have this classic, so-called classic photoredox catalytic cycle, a closed cycle, or the quantum yield is above 1, so above 100%, and this gives you the information there must be a light-independent chain mechanism in the back working independently from light. And for the Macmillan reaction, which is the alpha alkylation of octanol, for instance, using organic catalysis and photocatalysis, we found out that is not the best way to put a lot of light into this reaction. Instead, it's good to dim the light down to a minimum of energy. You see that on the screen here. The 30 microwatt energy gives you actually the highest quantum yield of about 35 here in this, and it's also time dependent, the time independent behavior, of course, of the reaction quantum yield. So the message I would like to tell you here is, don't use a lot of light in order to get a lot of product, which is not the right way to do. Sometimes it's even the opposite. The other point is that in a lot of cases, the back electron transfer is an issue. And for that, researchers are using additives like triethylamine in the oxidative case, in the reductive case, sorry, and thiophenol in the reductive case. And for that, we use a new concept, which is called, which we call photozymes, which are in fact small peptides that keep the substrate as long as forward and backward electron transfer have taken place. And this is the key here. And we use that for two different reactions, which are both alkylations or alkoxylations of alkenes. The one is the oxidative mode with respect to the photoredox catalyst. We use here aminopyrines, and the alkene is reduced, then it's protonated to the radical, and back electron transfer gives you the cation. And then finally, the alcohol is added to this cation. And this is, of course, the reason why we get here a Markovnikov product. In the opposite case, and that's on the right side of the screen, you excite perylene bisimides, and now you oxidize the alkane, and then you immediately add the alcohol to the radical, and back electron transfer together, of course, with back proton transfer gives you then the anti-Markovnikov product. And we have actually developed peptides for both of these types of reactions. And in both cases, no additive is needed anymore. We need this kind of clamp structure of the peptides, and we have a very low catalyst loading with respect to the photoredox catalyst, and this is about 0.5 mol%. We also try to use core substituted naphthalene diamides as organic photoredox catalysts. They are cheap, and they can be easily synthesized as long as you get this bromination done at the beginning, which is a kind of messy thing. But after that, you get a lot of interesting compounds. You can tune the optical and electrochemical properties. And you see that here, this is a range of these naphthalene diamides we synthesized in our labs, and they fit also to the range of different LEDs, depending on which excitation range you are using for your reaction. And the most important thing in our hands is that these naphthalene diamides are excellent spectroscopic probes. They form spectroscopically very well resolved radical anions and radical cations, and these can be used for ultra-fast time-resolved transient spectroscopy. And we do that again together with Eberhard Riedle in Munich, and to find out more about the mechanisms of organic photoredox catalytic reactions. The second class of compounds we try to use and develop for photoredox catalysts, for redox catalysis, are the phenothiazines. They again have the advantage that they can be synthesized very easily. They have a modular building. That means you can modify the core structure, you can modify the phenol ring, and the the unsubstituted N-phenyl phenothiazine has already a reduction potential in the excited state of minus 2.5 volts, which is quite astonishing. You can shift that by adding alkylated amino substituents to the phenyl ring in the power position, and with that we can actually shift the potential to minus 3.0 volts. You will hear about that later in this lecture by Fabian Weig. By adding another benzene ring, we actually can shift the excitation wavelength to the visible light, but losing, of course, of some of the energy in the excited state. Now we get back to minus 2.4 volts. With this very strong reductance, then with the amino-alkylated phenothiazines, we can actually activate less activated alkenes, like, for instance, the normal alkyl olefins. With that, we can actually convert them to the methoxylated products. And since we are not using acids or bases as additives here, we are quite broad with respect to the substrates. Then we can use all kind of functional groups here in the alcohol, including, for instance, the Bock protecting group in the alcohol or in the substrate. Both modifications are working here with this chemistry. Most importantly, as I promised at the beginning, the phenothiazines are also useful in order to activate SF6. You probably know sulfur hexafluoride from your basic chemistry courses as a very inert, completely inert and non-toxic compound. But it could be a useful compound in order to pentafluorosulfonylate organic compounds, and with that we need to activate it. And photoredox catalysis is one of the excellent ways to do this activation, because we can very precisely shift the reduction potential to a range that SF6 is precisely activated. And using that, we can actually pump an electron into the SF6, and it dissociates then into the SF5 radical. And with a second photoredox catalytic cycle, we can actually activate then the alkene and both radicals, and then are combining to this SF5 modified compounds. Either fluoride is trapping the compound or external nucleophiles like alcohols here. These SF5 compounds are extremely useful because the SF5 substituent is underexplored with, in comparison to, for instance, the trifluoromethyl substituent, because the synthetic accessibility is very much limited and mainly based on SF5 chloride, which is an extremely toxic compound, and I actually don't want to work with that in my lab. SF6 is non-toxic, and now we have a way to actually get SF5 compounds by a non-toxic way. This is just this slide is just a small combination of compounds that we are able to synthesize. Again, the alcohol is very flexible with respect to functional groups. If we add more alcohol, we get into a different mechanistic regime, and we get the cyclic compounds here, which are all of them pentafluorosulfonylated here, as you can see. And we can also develop a lot of follow-up chemistry, like, for instance, replacing the alcohol here on the right side by an acide, and you can go into amino compounds or click chemistry if you want. Having said this was my short introduction. I would like to hand over to my co-workers, to my two doctoral students, Fabian Weig and Desiree Steuernagel. Fabian will tell you a little bit more precisely about this very strong reducing phenothiazines. They cannot only be used to activate SF6, but there's much more chemistry going on here. And on the other end of the redox potential, you see on the right side, we use this perylene bisimides, this very electron deficient perylene bisimides, and Daisy will tell you a little bit more how you can actually convert or activate and convert silyl enol ethers. With that, I'm closing and I hand over. Thank you very much.
Yes, thank you very much for this overview over some of our photochemical methods. And having seen how strongly reducing aryl phenothiazines can activate substrates for the addition of alcohols, it became a goal for me in particular, and for me and Desiree, to use this for alkoxycyclizations. And of course, you may ask why. It's because cyclic structures impose a conformational constraints which lead to better binding to biomolecules. And in the literature, it's also correlated with a better bioavailability. That's why they are so common in pharmaceuticals. So 27% of all small molecule drugs and 15% of the FDA-approved pharmaceuticals bear such a oxyheterocyclic structure. And in particularly, 5- and 6-membered rings are of great interest, as well as some benzo-fused molecules, which you can see here on the right side. Yes, when it comes to ring closure reactions, there are some key effects going on, which can be demonstrated by this simple reaction over here. This is about how 5- and 6-membered rings are formed the fastest, and the speed of the reaction drops for smaller or larger ones. This is due to two different effects going on. So on the one hand, small rings form slowly because there's a highly strained system formed, which then leads to a higher activation enthalpy in the transition state. This is called like the bi-ring strain. You might be familiar with that. And on the other hand, there are large rings which form slowly because since longer the chain length gets, it disallows more conformations, and only a single one is leading to this cyclic transition state. So more degrees of freedom have to be given up. For example, in the case of the 4-membered ring, here the disadvantages of both of these effects come together. That's why they are formed so slowly. But how are oxyheterocyclic products formed usually, or are they usually made? Here you can see some examples from other research groups. These are some really good methods. For example, they allow the addition of additional substituents, as you can see here, or in the protocol after the Ishihara group. But as you can see, however, most of them are working with transitional metals, and as Professor Wagenknecht told you in the beginning, that's what we want to avoid. And yeah, with our new photochemical approach, those transition metals aren't required anymore. Yeah, but before we could start converting the substrates we are aiming for, we had to synthesize the corresponding chromophores, and the PBI system in particularly was initially challenging because since the solubility had to be optimized first to get a satisfactory catalytic activity. And as you can see here, in the end, this structure or this substituent, this aromatic substituent, gave the best solubility in the various organic compounds, which you can use for the photoredox catalysis. And so we've gone with that one. Our working group had already demonstrated the synthesis of these aryl phenothiazines, which Professor Wagenknecht also mentioned. And but in the course of this work, this synthesis could be improved so that this catalyst can now be produced quantitatively in very simple reactions. Yeah, but let's get to the photocatalysis finally. Our photocatalytic cyclization method shows a complete endo and exo selectivity, although both products are favored according to Baldwin's rules, and therefore a kind of a mixture is to be expected. But this is due to an intrinsic selectivity of the provided methods. On the one hand, you have this aryl phenothiazine catalyst, which works in a reductive manner. So after the excitation of the catalyst with a light of 365 nanometers, you get this excited species, which is then, because of this really strongly reducing properties, able to reduce this substrate. And after a proton transfer, an intermolecular proton transfer and a back electron transfer, you end up with this cyclic, with this switterionic intermediate, which is key to the cyclizations taking place afterwards, because it leads to the exo trig product in this case, and only to the exo one, because for a theoretical or hypothetical endo product, there's a primary cation required, which is not stabilized as this one in the benzylic position. On the other hand, the PBI catalyst works in an oxidative way. So after the oxidization of the substrate, there's such a competitive situation between the stabilization of a radical and the cation, and in such a situation, the radical is normally preferentially stabilized. So, which forces the cation to be on the terminal position, and which leads afterwards, in this place, which is different, the cyclization takes place directly afterwards, this oxidization step, and after back electron transfer, leading to the endo product. Yes, after we performed some photocatalysis to provide different ring sizes, as you can see here, we also isolated, or some byproduct also appeared, which we could isolate and characterize. And as you can see here for the method A, so the exo one with the Phenothiazines gave us, like I call it the eliminated products. And in the case of the method B, which goes to the endo cyclizated products while using the PBI catalyst, it gave us, in this case for the 7-membered ring, also such a 5-membered substrate. But the side products are quite good because they gave us a mechanistic hint, and for a good confirmation of the proposed mechanism, since they only can be formed via the corresponding intermediates. In the case of the method A, this switterionic structure, which I talked about, can eliminate back on the one hand to the starting material, which would be no problem because it can be activated again. But this one is not as stable as this one here, where the double bond is higher substituted, and this one is our side product, also referred to the side F product. On the case of the oxidative way, so the method B with the PBI, we can form this 7-membered ring and get, in this case, a side product which is shown here, and it's due to this situation where you have this cation and this radical in the same place, where the radical is preferentially stabilized. There you can cyclicize to the product, which is taking place very slowly because we have a large ring size with a 7-membered ring, but in a same order of magnitudes, like for the speed, there's a 1, 2, 3 H shift taking place to getting this intermediate, and out of that one we can cyclicize very fast to a 5-membered ring. That's because we have a quite good ratio, a ratio of nearly 1-to-1 between these 2 products. After that, we did some reactions with different functional groups, including electron withdrawing and electron donating groups. Also oxidizable and sterically demanding groups were tested. Overall, these are some satisfactory yields. And as I described in the beginning, benzo-fused products are particularly interesting, which is why we dedicated ourselves to them as well. And we can provide different ring sizes in benzo-fused products, as you can see here, up to 8-membered rings. And also we can provide this chromane, which is the basic structure of tocopherols, such as vitamin E. Yes, with the powerful reducing power of these Phenothiazines, up to, like Professor Wagenknecht said, minus 3.0 volts or minus 2.9 volts, we are currently working on the cleavage of difficult to reduce aryl chlorides, which gave us as a result such phenyl radicals, which offer us various synthetic possibilities. So yeah, just look out to some publications in the next few months, maybe in this topic. Yeah, with that, I want to hand over to my colleague Desiree, who wants to tell you a little bit more about this side of this spectrum, let's say it like that, with the PBI and the oxidation way.
So, good evening also from my side. Today I want to present you the latest results of my work in photochemical synthesis of acetals and ketols from silyl ethers. For this purpose, I'm working on the photocatalysis with electron-deficient PBIs. These allow not only to convert aldehydes but also ketones, as they are silyl ethers, into acetals at a wavelength of 525 nanometers. But why is that of particular interest? Organic compounds with a carbonyl group, in particular aldehydes, are of great synthetic interest as small building blocks for CC bond formation. However, their high reactivity also presents a challenge for multi-step synthesis, while these groups often need to be protected. For this purpose, acetals are common protective groups for carbonyls. Nevertheless, standard methods for acetalization use all different types of acids like hydrochloric acids, solid acids, or organic acids. In total synthesis, however, these acid catalyzed reaction steps are a major problem. In the case, molecules that already contain acid-sensitive groups are split off by this reaction step or undergo side reaction. Recent reports show the photochemical conversion of aldehydes into acetals by means of eosin Y or Schreiner's thiourea. However, both methods are in fact photochemical versions of aldehyde protonation, leading to the acetals and would not tolerate acid-sensitive functional groups. In comparison, Photoredox catalysis has proven to be an appropriate method for this purpose in order to avoid the use of acids in synthesis. In the following, I would like to present our results. In the first step, we tested different substrates with various substitutions. These substrates, including alkyl or phenylalkyl silyl ethers, were successfully irradiated, and the corresponding acetals were obtained in a yield of 76 to 100%. It is remarkable that the substrate, including the Bock protecting group, remains intact under the condition of this photocatalysis. Its conversion to the acetal results in a 76% yield. This clearly excludes the presence of acidic conditions during photocatalysis, which is a meaningful result because the photocatalytic acetalization is thereby proven to be orthogonal to the conventional acid catalyst method. The next step was to replace the TMS group with sterically more demanding silyl substituents such as TBDMS, TIPS, or TBDPS. For those substrates, a clear dependence on the steric demand of these larger protecting groups was observed with respect to their conversion in catalysis. Sterically less demanding silyl groups, such as TMS or TBDMS, can convert almost quantitatively, whereas the introduction of the TIPS group already lowered the yield to 13%. In addition, it was observed that the more sterically demanding the silyl group becomes, the stronger the formation of the respective ester is increased. If the TBDPS group is inserted, the conversion is even completely blocked because of too much steric hindrance. This results in the possibility of controlling the conversion of several carbonyl groups located in a molecule. Carbonyls that should be converted are substituted with small silyl groups such as TMS, and those that should be retained are protected with sterically more demanding silyls. In the next step, the catalysis was further investigated with the addition of different alcohols. There were again a clear dependency of the cyclical hindrance can be observed. The higher the hindrance, the lower the conversion to the respective acetal, and thus the amount of ester byproduct increases. Furthermore, it could be shown that various alcohols can also be used to introduce different functional groups into the respective molecule. This includes acid-sensitive such as alkenes or Bock-protecting groups. Again, our results show that we have found a very mild method for acetalization. The following mechanism was postulated for the conversion of silyl-enol ethers. Initially, a single electron transfer of the silyl-enol ether to the assumed to the excited PBI, and then methanol can be added to the resulting radical cation, and the resulting radical can then split off in silan to form the ester. The ester formation is already complete at this point, and the resulting silan radical closes the catalytic cycle by single electron transfer. To form the acetal, we postulate that the radical splits off a siloxane, and the resulting cation and to the radical cation, methanol is added again. Afterwards, the resulting radical acetal closes the catalytic cycle by single electron transfer. So in order to prove the catalytic cycle, the byproducts silan and siloxane were detected by mass spectroscopy. Going further, the catalysis was extended to the direct conversion of aldehydes. This could be converted into the acetals with good to excellent yields. This is a great success because, as mentioned before, the problem with the already known methods for converting aldehyde into acetal is the existence of acidic conditions, or at least the in situ formation of photoacids, which again excludes the presence of acid-sensitive groups in the molecule. This limitation can be overcome using our PBE catalyst, since obviously no acid are produced here. Therefore, functional groups were tested for their stability in catalysis, including substrings contained in the acid-sensitive Bock-protecting group or the hydrogenolytic benzyl group, as well as the CBZ protection. The presented results clearly show that neither acidic conditions exist during photocatalysis, nor hydrogen evolution takes place. All three protective groups remain intact under these conditions of this photocatalysis. However, it must be mentioned that the oxidation potential of the catalyst is too low compared to the aldehydes. And despite the absence of photoacids, the aldehydes can still be converted. So the question arises in which way the conversion is possible. Since the substrates could still be converted, further ones were tested in order to obtain additional information about the process. It was suspected that enol tautomerism is involved in the process. To further investigate this, the substrates shown here were tested. Where vinyl ethers lead to a good conversion, formyl groups or ester functionalities show no conversion. This confirms that the substrates require the ability to form CC double bond via ketoenol tautomerism in order to be converted. And these enols have a lower redox potential and can therefore be converted by our catalyst. Obviously, the next step was to test ketones. The ketones chosen for this purpose are structurally similar to the used aldehydes. However, they cannot be converted under these experimental conditions. Considering the ketoenol tautomerism, the fact that ketones are unsuitable for this for the catalytic acetalization is not very surprising. It is already known that ketones have lower ketoenol tautomerism than aldehydes. This could be the reason why no conversion takes place. Therefore, we wanted to try to convert the silyl-enol ethers of the ketones to force them into the enol form. In contrast, the ketones that herein shown, silyl ethers could be converted to acetals in good yields. However, the yields were lower than for the structures comparable to silyl-enol ethers from aldehydes. This intermediate step of converting the ketones into their silyl-enol ether made it possible for the first time to convert ketones into their ketals by photocatalysis. In summary, an acid-free photocatalytic method was developed using an electron-deficient PBI. With this, dilute enol ethers and carbonyl compounds can be converted into acetals or ketals. Aldehydes can be directly and selectively converted into the corresponding acetals, and dilute enol ethers can be converted into corresponding acetals or ketals. A broad substrate range as well as diversity in the selection of alcohols was demonstrated. The conversion of sterically demanding substrates and alcohols, as well as the tolerance towards functional groups, especially acid-sensitive groups, could be shown. By selecting the CLE group, it can be controlled whether the respective carbonyl should be converted into its acetal in a molecule. By this result, the repertoire of Photoredox catalysis could be expanded with regard to carbonyl chemistry. And yeah, with this, I come to the end and want to thank you for joining our presentation. And yeah.
Okay, thank you all for fantastic presentations. Do we have any questions from the audience? So far, I don't see any in the chat. I have a couple, but I want to give just a second more in case there are any more questions. Right, so I can go ahead and start. So Hans, the SF6 work is really interesting. I don't know if you can go to the mechanism that you presented on that. Yeah, there's certainly not a lot of really good methods to incorporate SF5 into organic molecules, which I think is a really important functional group because you know, really increased lipophilicity, that it gives molecules, and also, you know, it's extremely electron withdrawing. So, you know, a couple questions about this. So SF6, when it picks up an electron and does mesolytic cleavage, the interesting question is, you know, which way does the electron go, right? So, you know, obviously you show it going to the F minus or to fluoride, but you know, you could make a case that it could also go to SF5 to make an anion. Is there any calculations or anything to suggest, you know, how that mesolytic cleavage proceeds, and, you know, to what extent it goes, you know, the electron goes exclusively to fluoride?
Yeah, well, this is the key point actually you are asking. It depends actually on the excitation energy, how the SF6 cleaves into which reaction channel the SF6 actually goes. And I tried to find a slide on a different talk in order to show you that these calculations have been already done by a different group.
Okay.
And and that's the reason why our phenothiazines are so precisely activating the SF6 into the reaction channel that actually the SF5 radical is formed here. Let's see if I get this very quickly in the time frame. So you should see that here on the screen. I hope you can see that.
Can you switch the presentation mode?
Or it's the same problem.
That's better.
Exactly. So you can see here, if you activate the SF6 into the radical anion and you activate that by energies lower than 2 electron volts, then you end up in the channel where you form the fluoride radical. And actually there has been very nice work done by Timothy Jamieson and also Nagoni a couple of years ago, and now last year. Both of them activate the SF6 in exactly that reaction channel, and that gives you then only fluorinated compounds. So let's say not only, it's more in our sense only, and it's a deoxyfluorination than what you observe then. So Jamieson uses the iridium complex that is drawn here on the slide. And in our case, we activate the SF6 by our phenothiazine. So we go in, we put lot more energy into it, and with that we open another reaction channel, and that actually cleaves into the SF5 radical, and that has been shown here in this particular reference in 2015, and the people have calculated that.
That's interesting. So does it go to, basically, are you populating a higher anti-bonding orbital with that electron? Is that the thought?
Yeah, 3, yeah, something like this. Yeah.
Okay, interesting. The other question I had was, so if you go back to that mechanism slide, so you have the SF5 radical, and if I'm not mistaken, you have that reacting with the alkene cation radical, which is, I would say, somewhat unusual mechanism, but had you considered the opposite possibility where it's just reacting with the neutral radical or neutral alkene, because polarity wise it's matched a bit better than than the electron deficient SF5 reacting with an electron deficient cation radical. I just wondered if you considered the opposite possibility.
Of course we did that, and actually that's our mechanistic studies here, a little bit of mechanistic studies. We have done this a little bit earlier. Well, what you mean is a kind of Giese type reaction, that the SF5 radical actually attacks the alkene, and then you get the back electron transfer, which would be a much simpler mechanism, of course. But if we form actually the phenothiazine radical cation in the dark, we can do that, for instance, with this nitrosium PF6 compound, and then we keep that in the dark. We don't see any loss of the spectroscopic signature of the phenothiazine radical cation in the presence of the alkene substrate. That means that the central step here, the oxidation of the alkene by the back electron transfer of the phenothiazine, does not work. And we need a second excitation. If we excite that sample that we have chemically prepared at 525 nanometers, we get the phenothiazine in the radical cation of the phenothiazine excited state, and then it's actually able to oxidize the substrate. And then we see that, although it's very unlikely that, I mean, a radical recombination mechanism, I get this question a lot of times actually, is very unlikely. But we think that the radicals are keeping together as long as then the reaction proceeds, and that's what we think actually. But we are not sure here at this point, of course.
Okay, thank you, Fabian. Question for you: if we can go to your presentation on the hydroalkoxylation chemistry. I think we talked a little bit about the mechanism on that one.
Yes, can you tell me which slide do you mean?
That one. Oop, you had it. Yeah, yes. That one. That's a good one there. Yeah, so really nice chemistry, and I love how you can control Markovnikov versus anti-Markovnikov in terms of either reducing or oxidizing the substrate. It's pretty interesting.
Yes, it's exactly the same chemistry with that one, yeah.
Yeah, so my question is on the anti-Markovnikov side. I was a little confused on so once the alcohol addition occurs, you lose a proton, you get to that radical, that benzylic radical there. Are you proposing that that's a reduction event to the carbanion on the right side? So on the so reduction to the anion and then proton transfer. Have you looked at what the in terms of the electron transfer event, what the energetics are for that step? Because that seems a bit uphill to go from the radical to the carbanion there, even though it is benzylic. I'm just curious if you all had considered just a simple hydrogen atom transfer step, which is what we propose in the anti-Markovnikov chemistry that we've done based on the mechanistic results. So I'm just curious of why that particular mechanistic step.
Yeah, well, I have not calculated this one, so it's more like intuitive. So, but yeah, it could be the another way around. You're right, but I think in terms of the cyclization which is taking place here, this one needs to be right after the oxidization, and where we came out is like a protonated. This protonated one is left after the cyclization, so this protonated oxoheterocycle, and therefore I think it's quite acidic because yeah, a protonated oxygen atom then can easily like give up this proton in the proton transfer to form this one, and after that the electron back transfer can take place and get the proton like back in this position then to form product.
Okay. Okay. Thank you. I have a few questions from the audience now, and maybe you all can choose who answers these. So one of the questions was, I wanted to know, have you synthesized PBI framework catalyst and how you have chosen this reaction for the PBI catalyst?
I think I can answer this. It's no, I mean, we have simply seen the equivalence of an alkene with an enol ether. So an enol ether is a very electron-rich alkene, and the PBI is a compound that forms very stable radical anions, and that fits together. That's a simple basic idea behind that.
Okay. Next question is, basically in the SF6 work, the question is, alpha aryl or phenylalkenes or styrenes work. Do other alkenes or other substrates work in this reaction?
That's exactly what we're exploring now. At the moment, we are fixed to alpha methyl and alpha phenylstyrenes, but we try to get this done also with other alkenes. I'm not sure if we can be able to convert alkyl alkenes, but we are working on that right now. Yeah, that's exactly the point.
Okay. Looks like we have two more questions. Is there any possibility of the photocatalyst to give energy to speed up the reaction alone, rather not to involve the SET process, and thereby forming the product in excellent yield? I'm not sure I followed that question. Maybe you do.
I'm not sure what this question means actually. No, I mean the key is of course back and forward electron transfer, forward and backward electron transfer on the components of the Photoredox catalytic cycle. And as we have seen in the previous talk, if we have this EDA complexes, the back electron transfer is in a lot of cases too fast, and then you don't form the product. And in our cases, in a lot of cases, the back electron transfer is too slow, and then we have to add these additives in order to have electron shuttles. But I think I hope this answers the question. I'm not sure about this.
Okay. Yeah, I'm not sure. The last question was regarding, I guess, on this slide, what the redox potential of the exocyclic molecule is. I'm not sure if they're referring to the alkene starting material, maybe. That's what I'm going to guess.
Yes, I can take that one maybe. Yeah, of course, these are similar, or these are both the same starting materials, so they have the same electrochemical properties. But on the one hand, you have to look at the oxidization potential, and on the other hand, you have to look at the reduction potential. And as these are styrene derivatives, they are quite similar to like methylstyrene. So it's round about 2.1 volts. I think it's in that region. So there's no big influence of this alkane chain with a hydroxy group at the end.
Right. Yeah, there's a Synlett resource from our group that talks about redox potentials of organic molecules. So if you're interested in looking at that, we have about 250 common organic molecules that we measure redox potentials for, and you'll find some of that information there as well. Okay, I think that that concludes the discussion for the second talks. Thanks again to Hans, Fabian, and Desiree for a fantastic presentation. I really appreciate your time today and sharing your science with us. Right.
Maybe one last. We haven't mentioned our funding agency, which is the Deutsche Forschungsgemeinschaft, of course. We should mention this because they fund our research. And I didn't mention one particular person, who is David Rombach, who actually did all the SF6 chemistry in my group. And both of them should be acknowledged at the end. That's all. Thank you.
Great. Thanks, Hans. All right. Thanks again, everyone, for joining us today. We're really, it's been a great morning, afternoon, or evening, depending on where you are in terms of the science, and hope you enjoyed it. Catherine, did you have any concluding remarks for us?
Yeah, so before we finish, can everyone switch on their cameras? I guess everyone is there already. I heard that Todd has unfortunately left already because he has to give another talk somewhere else.
He's a busy man today. Yeah, he's at University of Delaware today.
Okay, yeah. So everyone's here. So before we finish, I have a little surprise for you. It's nothing really bad. So at
I hope not.
No, don't worry. It's not bad. So at the end of every WebCheminar, we ask all of our speakers a question. It's the same question every time. And you can answer it if you want to answer it. If not, then not. Doesn't matter. Yeah. So the question is, what is the biggest misconception about organic chemistry? Okay, who wants to start?
Oh la la. Biggest misconception.
At least I think in America, one of the biggest misconception is that like people are like, oh no, there's chemicals in the food and stuff, but it's actually like it's all chemicals, I think that's the biggest. People are like afraid if something's a chemical, they're afraid that it's a chemical, So that I would say is the biggest misconception. At least I've come across the most, like not having the knowledge that like everything is made up of chemicals, and just because something's a chemical.
Yes, of course. Yeah, that's what I teach always. Yeah. Maybe. Yeah. One misconception in organic chemistry is that it's sometimes considered to be a mature science, and I think this is not the case. As long as you haven't done the synthesis, you don't know if it's working or not. There could be predictions on the paper or by calculations in the best case, but as long as you haven't done the reaction, you can't tell if the reaction works or not. And there are so many parameters you can change: temperature, pressure, catalyst, whatever, concentration, solvent, and so on. This is a multi-parameter problem, and you can't really predict that at the moment, I would say. So this is probably, from my side, always the reason why I think organic chemistry is an important research.
Yeah, to kind of follow up on what Hans said, I agree with that. I'd add that, I think a lot of different fields of science think that, organic chemistry is pretty straightforward. We can basically make whatever we want. And oftentimes what a lot of people find is that the organic chemistry step is really the limiting step in terms of doing the science they want to do. And so, I see that as an opportunity for all of us to contribute new methods, new ways of thinking about constructing complex organic molecules. And so that certainly gives us plenty of work to do.
Exactly.
Thank you. Anyone else?
Quite hard to say something, but I mentioned, or I can imagine something from my bachelor's time, where everybody in the organic chemistry told us there is no carbon atom with 5 bonds, but it actually can be there. So that's one little one, but yeah.
Okay, everyone happy? Okay, then then of course I have to thank everyone here before we finish now. Thank all the speakers who did really great, interesting presentations. Then of course Dave, you did great as a chair, and then of course the Thieme chemistry team who are working in the background to make all the technical things happen. And then the attendees, of course, Thank all the attendees for listening, and I hope to see you again, October the 12th, electrochemistry. Yeah, that will be great. Okay, then thank you everyone, and have a nice evening, day.
Thank you.
Okay, bye. Thank you very much.
Bye-bye. Take care.